So new definition, two matrices, A and B, are said to be row equivalent if one can be produced from the other by performing a finite sequence of elementary row operations So evidently, every matrix A is row equivalent to itself, since a sequence of elementary row operations that produces the matrix A from itself consists of a pair of inverse operations as demonstrated in the previous example. Now, if A is row equivalent to the matrix B, then the matrix B is row equivalent to A, since we can perform the inverse operations in reverse order that produced B from A to produce A from B. Further, if A is row equivalent to B and B is row equivalent to C, then the matrix A is row equivalent to C, since the sequence of elementary row operations that produced B from A followed by the sequence of elementary row operations. That produced C from B is a sequence that produces the matrix C from the matrix A. So we have demonstrated that row equivalence is an equivalence relation that is reflexive, symmetric, and transitive. So new definition: a matrix E is called an elementary matrix if it can be produced by performing a single elementary row operation on an identity matrix Now, an elementary matrix encodes an elementary row operation in matrix form And what I mean by encodes an elementary row operation will become clear in the next theorem. But first, we need a fact that we will use repeatedly in the proof of that next theorem. So recall that the ith row of the matrix product A times B is the ith row, or the ith row vector, of the matrix A times the matrix B. And so the ith row vector of the product, the identity, times B is the ith row vector of the identity times the matrix B, and this must be equal to the ith row vector of the matrix B, since the product of the identity times the matrix B is the matrix B. So next we prove a theorem. Let E be the elementary matrix obtained by performing a certain or specific elementary row operation on the M by M identity matrix, and let the matrix A be an M by N matrix. Then the product E times A is the matrix obtained by performing the same elementary row operation on the matrix A that produced the elementary matrix E from the square identity matrix of order M. So proof. Now there are three types of elementary matrices, and so we have three cases. So case 1, let C be a non-zero constant, and suppose that the elementary matrix E sub 1 is produced by multiplying the ith row of the identity matrix by the non-zero constant C for some fixed index I. The ith row vector of the product E sub 1 times A is the ith row vector of the elementary matrix E sub 1 times the matrix A. The ith row vector of the elementary matrix E sub 1 is the constant C times the ith row vector of the identity matrix times the matrix A. And so this is the constant C times the ith row vector of the matrix A. Now for the index j not equal to I, the jth row vector of the product E sub 1 times A is the jth row vector of the matrix E sub 1 times the matrix A, and the jth row vector of E sub 1 is the same as the jth row vector of the identity. And so we have the jth row vector of the matrix A. That is, the product E sub 1 times A is the matrix obtained by multiplying row I of the matrix A by the non-zero constant C. So, second case, suppose that the elementary matrix E sub 2 is obtained by interchanging row I and row J of the identity matrix for some fixed indices I and J, the ith row vector of the product E sub 2 times A is the ith row vector of E sub 2 times the matrix A. The ith row vector of the matrix E sub 2 is the jth row vector of the identity, and so this is the jth row vector of the matrix A. Now the jth row vector of the product E sub 2 times A is the jth row vector of matrix E sub 2 times A. The jth row vector of E sub 2 is the ith row vector of the identity, and so this is the ith row vector of the matrix A. And for an index k not equal to I and not equal to j, the kth row vector of the product E sub 2 times A is the kth row vector of E sub 2 times A. The kth row vector of E sub 2 is the same as the kth row vector of the identity, and so this is the kth row vector of the matrix A. That is, the product E sub 2 times A is the matrix that results from interchanging row I and row J of the matrix A. So case 3, let C be a non-zero constant, and suppose that the elementary matrix E sub 3 is obtained by adding to row J of the identity matrix the constant C times row I for some fixed indices I and J, the jth row vector of the product E sub 3 times A is the jth row vector of the matrix E sub 3 times A. The jth row vector of the elementary matrix E sub 3 is the constant C times the ith row vector of the identity plus the jth row vector of the identity. So applying the distributive law, we have C times the ith row vector of the identity times A plus the jth row vector of the identity times A. And so this is C times the ith row vector of the matrix A plus the jth row vector of the matrix A. And for any index k not equal to j, the kth row vector of the product E sub 3 times A is the kth row vector of E sub 3 times A, and the kth row vector of E sub 3 is the same as the kth row vector of the identity. And so this is the kth row vector of the matrix A. That is, E sub 3 times A is the matrix that results from adding C times row I of the matrix A to row J of the matrix A. And therefore, in any case, the product E times A is the matrix that results from performing the same elementary row operation on the matrix A that produced the elementary matrix E from the identity.